A traditional helicopter commute from Manhattan to JFK will cost you about $500. But the companies building the next generation of electric air taxis project that they can reduce that exact same trip to just $70. To understand why a traditional helicopter ride is so expensive, look at the operating costs of the machine itself. Running a standard turbine helicopter requires over $300 an hour just to cover liquid fuel, overhaul parts, and intense periodic maintenance. Add in the real estate. Leasing premium waterfront helipad space in an urban center is so expensive that landing fees make up roughly 40% of the overall ticket price for a traditional trip. This chart compares the operating expenses of a gas helicopter with an electric vertical takeoff and landing aircraft, or eVTOL. By swapping a turbine engine for electric motors and batteries, the hourly cost to keep the vehicle in the sky drops by over 30%. The math scales further with utilization. Because these electric aircraft are quieter and cheaper to run, they can theoretically fly up to 2,000 hours a year. Operating around the clock allows companies to spread out the initial $1.3 million manufacturing cost over thousands of flights. Divide those reduced operating costs by 3 or 4 passengers flying in a continuous loop, and a $70 ticket becomes a strict mathematical output. The numbers work, provided the industry can reach massive operational scale. Reaching that scale requires clearing a specific hurdle. The primary barrier keeping these aircraft grounded today is no longer battery chemistry or rotor noise reduction. The actual bottleneck is regulatory certification. The Federal Aviation Administration is the ultimate gatekeeper. If the agency forces air taxis to meet the exact same standards as commercial airliners, the financial viability of the industry collapses. If they loosen the requirements to match automotive standards, safety drops and the public won't fly. Currently, the FAA lacks a single, unified framework for these novel aircraft. This forces every single manufacturer to negotiate their own custom regulatory pathways with the agency to get permission to fly. Securing a path to market depends on balancing the speed of innovation with the rigid safety requirements of federal law. Two of the earliest trailblazers, Joby and Archer, are pushing the boundaries of all-electric aviation through a demanding bespoke certification process known as Part 21.17b. This is a provision that lets the FAA stitch together a custom certification basis for aircraft that don't fit neatly into existing airplane or helicopter categories. Joby has pushed all the way to Stage 4 of the FAA's 5-stage process. This is the 4-credit testing phase, where every structural load, flight control, and individual subsystem faces strict physical oversight from federal regulators. While Archer is also pushing their hardware through testing, they are simultaneously stockpiling operational certificates, like Part 135. Part 135 is the specific FAA certification required to operate an on-demand commercial air carrier service. Archer is building a ready-to-launch airline infrastructure while they wait for their hardware to clear. Meanwhile, a company called Electra is taking a different approach. Instead of a vertical takeoff vehicle, they are building a hybrid electric short takeoff and landing aircraft, or eVTOL. Because Electra's aircraft takes off and lands conventionally on a runway, even a very short one, it fits cleanly into Part 23. Part 23 is a mature certification framework used for standard small aircraft, meaning the FAA doesn't have to invent new rules to evaluate it. Joby and Archer are forging completely new regulatory frameworks for all-electric vertical flight. Electra is betting that a conventional, lower-risk shortcut will get their vehicles certified and generating revenue much faster. Certifying the hardware only solves half the equation. If thousands of new air taxis suddenly launch over a major city, traditional air traffic control would buckle under the volume. This diagram illustrates the FAA's proposed solution, outlined in a recent Concept of Operations document. They created a system called Extensible Traffic Management, or XTM. XTM is a highly automated, cooperative environment designed to run parallel to standard air traffic services. This schematic shows how XTM physically applies to the sky. The FAA will establish Urban Air Mobility, or UAM corridors. These act as dedicated, invisible highways suspended over suburbs and cities, keeping the new air taxis completely separated from traditional commercial planes. Inside these point-to-point corridors, pilots don't talk to traditional air traffic controllers. Instead, the aircraft connect to a federated network of independent service providers, constantly sharing their flight paths to cooperatively dodge each other in real time. To make a $70 flight possible, the sky itself has to evolve from a centralized airspace managed by humans on radar to a decentralized, automated data network. This FAA timeline starts in the bottom left crawl phase, low-tempo flights with human pilots under current rules. As demand grows, we move to walk and run phases. High volume activates UAM corridors, pushing aircraft toward remote piloting and automation. The raw economics of this industry rely entirely on reaching that top right corner. The highly profitable mass transit $70 commute only works when the network is flying at maximum density. The true winners of the advanced air mobility revolution won't be companies with the sleekest designs, but the ones who successfully integrate into this invisible regulatory grid.